Good morning, everybody. Edward Zhu from Hong Kong, and my co-author, Professor Sun, and I would like to thank the organizers for the opportunity to give this talk. So today I'll be presenting my research, a pose-based walking/running coach system for cerebral palsy patients using artificial intelligence and computer vision. So the following 5 contents will be discussed. First of all, the use case and problem, followed by the proposed solution, 3 experiments, and a discussion on the new contributions to the field of clustering and gait analysis. And then lastly, some limitations and future work on diagnosis will be discussed. So to introduce the problem of cerebral palsy and gait analysis, cerebral palsy, or CP in short, is a neurological disorder that affects your movement and balance. So it can affect somebody's gait. So gait is basically the walking pattern, and by causing abnormal muscle tone, spasticity, uncontrollable movements, etc. And about 1 in 3 children with CP cannot walk. However, if you have early intervention, you can develop mobility over time. So CP can cause a wide range of gait abnormalities, such as jump gait and crouch gait, which is pictured on the screen, which are all often associated with specific subtypes of CP. So being able to objectively evaluate a patient's gait is very important for intervention because you can identify the underlying causes. You can subsequently diagnose what subtype of CP they have, and then to develop appropriate interventions. So typically, computerized gait analysis is preferred over human observation because it's repeatable and it's more objective. So one of the most commonly used solutions is called clinical gait analysis, or CGA. So in short, this is a process that's held in clinics and combines a large amount of data as pictured on the screen. And the limitations are that it's usually quite expensive, and a lot of the equipment is not available in the average day-to-day clinic, which means that this process is excluded from many different patients. So I wanted to investigate the research question: how can an affordable and effective method be created to provide gait analysis data to cerebral palsy patients? So to summarize the main proposed solution, this work utilizes k-means, a clustering algorithm, and pose estimation to analyze 2 different videos. So one is of the CP patient walking, and another is of an expert that shows the proper gait. And the purpose is to determine the differences in the range of motion. So if you can see on the screen here, the patient on the left is somebody is a CP patient, and they have an issue where their knees are bending inwards. So like an average person, when they're standing still, they should have their hip, their knee, and their foot forming a straight line. So the angle should show 180 degrees. However, for this patient, it's about 160 or 140 degrees. So in short, my system would be able to identify these differences in range of motion. And this data is very useful for self-diagnosis. So there are 3 main components of the system. There's the backend, front end, and storage. So onto the backend. So all the backend is written in the Python free programming languages, and it's held on an Amazon Web Services cloud server. So in this work, we use MediaPipe, which is a cross-platform computer vision library that was developed by Google. And more specifically, we used the Blaze Pose GHUM 3D model. And this model basically is able to identify the location, the 3D location of 33 pose landmarks with high accuracy. In this work, however, we only use 12 of the landmarks because we're excluding some of the points which aren't necessary. So in order to prepare a certain video data for analysis, we first utilize a library called OpenCV, which is also a computer vision library on Python. So what this does is that we create an algorithm to resize the dimension of the video such that the 2 videos we're comparing have the same dimensions and length. And then we convert all of their color schemes to RGB. And then we convert the video path, say all of them to the standardized MP4 file. And then we create a list of video frames from a specific video. And then later on, we use MediaPipe to extract the coordinates of 12 key landmarks, such as your left shoulder, or like your left knee, etc. And then we output a list of pose vectors that can be analyzed later. So to summarize this backend, we take a full unprocessed video inputted by the user, and then we turn them into a list of frames seen here. And then we process them using MediaPipe into a list of pose vectors. So now that we have frames for both videos, we want to find a way to compare them. And to compare two videos, we need to basically, the methodology is we're identifying matching frames or representative frames that capture the same key movements between the two videos. So like, for instance, we're finding which frames in both videos depict the person's heel striking the floor. So we considered three possible methods to create these matching frames. The first is a chronological comparison. So what this is that we're comparing frame 1 of video 1 and then frame 1 of video 2, frame 2 of video 1 and frame 2 of video 2, and etc. So this way we're basically creating matching frames according to their chronological order. So however, this solution typically provides inaccurate data because the two videos may have different numbers of frames depending on their frames per second. So some videos may have 60 frames per second and some may have like 24. And another possible method is interval comparison, which is where we're basically picking matching frames for like every fixed time interval and getting about 5 to 10 of these representative frames in total. So, however, this is usually not very effective or accurate because for patients with CP, their movements can be uneven. So they may move like one leg faster than the other. Some of their gait cycles may be faster than the other. So choosing matching frames per every fixed time interval would not be optimal. So instead, we propose using the k-means clustering algorithms to group pose vectors, and then we extract the centroids as the key representative the representative key poses. So in the image on the right, we have basically a diagram of this in action. So we have, in this case, we've clustered the, so in this case, we have created 5 different clusters to group the video frames of a patient. And each of the red X's represents a centroid of the cluster. And then these are basically the key frames that we're going to be using for comparison. So to go into more about what k-means is, the k-means clustering algorithm is an iterative process that partitions a data set into k different clusters. And we're ensuring that each data point is assigned to only one single cluster. And that's what makes it different from other clustering algorithms like fuzzy clustering. So in this project, we use this specific process where we first basically sort n different frames by their timestamps, and then we pick a few of them as the initial centroid frames. And then we use the Euclidean distance function to basically iterate over and over again until the centroids remain the same. And then in that case, we just end the algorithm. So this way we're able to find the cluster. We're basically able to, the clustering number is 20. So we have a bunch of video frames with their pose data, and then we put them into 20 distinct groups and identify their clusters. So what we do after this is that we do the k-means process for both the user video, inputted video, and also the expert video that shows their proper form. And we basically look at the cluster centroids that are the most similar, and we compare their range of motion differences or joint angle differences. So in order to calculate these joint angles, we simply use this mathematical formula where we have 3D coordinates A, B, and C, where B is the middle point. So for example, like A may be the 3D coordinate of your shoulder, B may be the 3D coordinate of your elbow, and C may be the 3D coordinate of your hand. And using this function, we're then able to find the angle in your elbow. So any joint angle differences that are exceeding 20 degrees are flagged. And here is basically a screenshot of the code where we have all of the angles that we're using. So to discuss the front end or what the user is interacting with, the application's user interface is developed using Flutter, a specific language on the platform Android Studio. And since Flutter is compatible with both iOS and Android devices, this makes this application available on a large amount of devices. So the process of the user experience is that the user is first prompted in the home page to choose whether they want to input a video of them walking, jogging, or running. And then they're presented with a list of expert videos that show the proper form. And then they basically choose one of these that best matches their recording and pace. So then when the user inputs their video, is about 3 to 5 seconds. It's filmed from the sagittal plane. So sagittal plane is basically a side view. So the application would then send that video of the patient onto the Amazon Web Services backend. And then that's where like all the programming is. And then when the analysis is complete, it sends the output into Firebase, which is basically it's another cloud server that's developed by Google. And then basically the application receives the output from Firebase and displays it as you see here, where there's first of all a montage between the matched frames between the user and expert videos. And then there's also a list of which of the joint angle differences exceed 10 degrees. And basically these show basically what needs to be improved on. So if their angle difference is quite large, then you can deduce that this is kind of an area of improvement. And some two additional pages are the historical recordings page, where users are able to access their past recordings and analysis results. And then there's also the graph data page, which displays the joint angle difference on the y-axis and the date of analysis on the x-axis, which allows the users to track their progress over time. So this front end is user-friendly. It's quite simple and straightforward to use, and it provides a comprehensive tool for gait analysis and allows for monitoring of improvements over time. So to discuss the three main experiments conducted is, first of all, we wanted to assess the effectiveness of the k-means clustering algorithm. So there's a metric called silhouette score, which is a numerical score from -1 to 1, which basically determines how similar the data points are within their own cluster compared to other data points in other clusters. And -1 basically means that this k-means clustering was very inaccurate, and 1 is the most accurate. So what we did in this experiment is that we used two different videos. So one of them is of a video of a cerebral palsy patient walking for 7.6 seconds, and another is of a medical professional with showing the proper form that's walking for 6.9 seconds. And then we basically used the k-means process described earlier, and we calculated the silhouette score. And we found that generally speaking, for k-means clustering, there was about a 0.5 accuracy new silhouette score. And since the silhouette score is calculated from a range of -1 to 1, where 1 is the best, 0.5 is generally considered to be quite accurate. So we also did the same process for a different algorithm called chronologically closed frames, which is basically another clustering method that was described earlier that kind of acts like a control. And we found that the silhouette score was significantly lower, which is about in the 0.35 range. So this basically demonstrates the accuracy of the k-means clustering in this specific use case. The second experiment was to compare the performance of supervised learning models with the k-means clustering approach. So in order to do this, we collected a few of these supervised algorithms, which include nearest neighbor, nearest centaur, nearest component, multi-class SVM, basically different models for supervised learning. And what we did is that we collected approximately like 100 videos of just people walking, including CP patients, and then we dissected them into individual frames, and then we manually labeled them from 1 to 5, depending on what part of the gait cycle the frames depicted. And then we fed this into these 4 algorithms, and we calculated their confusion matrices and accuracies. So we can see that generally it's about like 0.6 to 0.7 or 60 to 70% accuracy, which is generally considered to be kind of low. And given that a supervised algorithm requires a large amount of data in order for it to show high accuracy, and compared to an unsupervised algorithm, which does not require pre-fed input, this justifies why, and considering the low accuracy shown in this experiment of supervised models in our use case, this justifies why we would want to use a clustering method instead. And then we also conducted a comparison between different computer vision models. So in this case, we compared MediaPipe and Yellow V7. So Yellow V7 and MediaPipe are both computer vision pose detecting models on Python. And there are a few differences between them, but largely they do the same thing. But Yellow V7 is multi-person, while MediaPipe can only detect one single person. And so in this experiment, what we did is that we basically passed a few images into both of these computer vision models and wanted to, 2 videos. I wanted to see which of them had the output that was had higher FPS or frames per second. And a higher FPS means that the output is better, and lower means worse. And we found that for Yellow V7, they had a much lower FPS of about 8.1, while MediaPipe had about 29.2 FPS, which justifies why we use MediaPipe as compared to a competing computer vision model. So to discuss the related works, and there's been a lot of research and studies in the literature field of using clustering algorithms like k-means for gait analysis. And clustering has been used for this specific use case for quite a while, even since like the 2000s. And here are a few studies that I found which specifically focus on the use case of cerebral palsy gait analysis. So the popularity in general of using like machine learning algorithms for gait classification is that it removes a subjectivity, and it's also a subjectivity in the process because a lot of the times the diagnosis it varies depending on the clinician's experience and their own subjective opinions, which can not make it repeatable. So there have been many studies on the specific field of gait clustering for gait analysis. Most recently, in a 2023 study, unsupervised machine learning effectively clusters pediatric spastic cerebral palsy patients for determination of optimal responders to selective dorsal rhizotomy. So by Ho et al. So to summarize the study, it uses k-means to cluster patients with a specific type of CP called spastic CP into 3 different groups: best responders, good responders, and moderate responders, to see which patients respond the best to a specific type of surgery. And then this clustering was based on the following parameters, such as spasticity of lower limbs, the number of target muscles, and also the sagittal plane data. And many studies seek to automate clinical gait classification processes. So one of the most widely recognized classification processes used by clinicians is the RADA classification system. So what this does is that it categorizes gait patterns of spastic patients into 4 different groups based on observation. So in the 2020 study, Darbandi et al. Basically created a system that would automate the process of RADA classification using fuzzy clustering, using basically sagittal plane data. And the results showed that it was quite accurate. If I remember, it was about like 94% accuracy. Basically, the 4 groups are, I think, jump gait, crouch gait, a true equidus, and apparent equidus. And this model was able to correctly predict a certain patient's like gait pattern based on some parameters, based on the above parameters. So there also have been some older studies in this field. One from like I think 2008 was using fuzzy c-mean algorithms and principal component analysis, where, to summarize, the study involved inputting video data of regular children and children with spastic diplegia CP, and then the findings show was that their system was able to distinguish between the gait of a regular child and the gait of a child with a CP, spastic CP. However, it was not able to go further and identify what specific type of spastic CP the child has. And a similar result was found in the study determination of gait patterns in children with cerebral palsy and cluster analysis, which uses the k-nearest neighbor KNN algorithm, which was able to successfully determine distinguish between a regular child's gait and a child that has been affected with some type of CP, was not able to go further and determine what specific type of CP they had. So to discuss some of the limitations of this research field is that, first of all, is that there's a bit of a limited scope, in that a lot of the studies are applicable to like a specific subsection of CP patients, which are children with spastic diplegia CP. And many studies are only about differentiating CP patients with unaffected children, and there yet is a study that is able to be applicable for CP patients in general. Furthermore, there's also limited research on clustering that relies only on sagittal plane data. Like, for example, some studies rely on additional clinical data like spasticity of muscles. And what this means is that it reduces the possible use cases of the application or of the study, because like data such as the spasticity of your muscle needs to be collected in very specific medical circumstances, which means that in many clinics that would not be able to be used. And on a similar note of data collection is that many studies utilize data that is collected from specialized equipment collected at specific clinics that have this equipment, which means that for like the average data clinic, they will not be able to use the results of that study. And furthermore, all of the infrastructure was like the new contribution of our study was that a lot of the infrastructure that was described in the previous studies is now moved or transferred to the average common mobile phone, where you're able to collect data with basically your phone camera, and also able to access gait analysis results from basically your mobile phone anywhere you are. You don't need to have specialized medical equipment in order to receive that data. So I also did some research on this supervised algorithms that have been used for gait analysis. And one specific one was from 2019 called Application of Supervised Machine Learning Algorithms in the Classification of Sagittal Gait Patterns of Cerebral Palsy Children with Spastic Diplegia, where researchers Zhang and Ma developed a classification system with ANN, which is artificial neural network, for identifying gait patterns like jump gait and crouch gait using sagittal plane data from children. They collected data from 200 children at this specific rehabilitation center. So the limitation of this like supervised algorithms for gait analysis is that so far an accurate system that can analyze gait input from patients with an unknown diagnosis has yet to be developed. Like a lot of the research has been specifically about one type of patient with spastic, which is patients with spastic diplegia. So yeah, a system that is able to be used for all types of CB patients has yet to be developed with supervised algorithms. And a bit more on machine learning and just pose analysis in general. There have been research, like for example, on like the classification of Bulgarian folk dances, which utilizes kinetic sensors and machine learning algorithm to basically classify them to specific types of dances. And another one was a sports application by researcher Mora, where they used visual data from tennis players and fed them into a neural network to determine what specific tennis action the player was showing. And generally speaking, these many studies which utilize machine learning and pose analysis require data or parameters that are collected from specific equipment, as mentioned before. And our study differentiates this because you're able to collect data just from your remote phone. So to conclude, in the study, we proposed a system and algorithm that can analyze the walking and the gait of a cerebral palsy patient. We used a k-means clustering algorithm to identify the representative frames from a user's inputted video. And then we also developed a complete mobile application where users can get gait data and see their improvement over time. And the experimental results show that this low-cost clinical gait analysis system has shown to have quite like a lot of accuracy. So to discuss, one of the limitations is the runtime limitation, which is that the application can sometimes take about up to 20 seconds to show the data, which depends on the quality of the user's video input. So for example, videos that were captured or taken from a non-sagittal plane, which is basically a non-side view plane, they take longer to process, which can negatively impact the efficiency of the algorithm. And the future work will focus on how we can take a video that was not taken from the sagittal plane and convert it into something that's interpretable by the algorithm, and possibly exploring alternative clustering algorithms. And also to incorporate more efficient backend service in AWS could be another solution to improve the performance of the application. So another point on the conclusion is future work on diagnosis. So currently our application's gait analysis system is limited to showing the differences in your joint angles. So while users can use this data to self-diagnose themselves using established classification systems, a better system would automatically interpret this output the gait data and automatically inform the user of their potential diagnosis and recommend appropriate treatment options. And in this case, supervised machine learning can be leveraged using open source data of cerebral palsy patients that have their video and of them walking and a label of their diagnosis to develop the system. And thank you everybody for listening. And this is my contact information.